Hey class, Mr. Hanji here. For today's lesson, we are going to be taking a look at section 1.4, which is going to deal with reasoning and proof. Now, just to make you aware, section 1.4 is the final section for Module 1, and what that means for you is that you need to expect a quiz coming up soon. So I just want to make you aware that it's the final section and that a quiz will be on the horizon. So, with that said, we are going to jump into our lesson for today. Now, reasoning and proof is going to give us an introduction into inductive and deductive reasoning and how to go through and prove something to be true or not. So, with that said, let's get going. For today, we only have one learning goal, and our learning goal is you will be able to use reasoning to prove a statement true. So, we're going to go through and talk about how we can do that and the different process. Alright, so let's jump in. First thing we're going to take a look at is a conjecture. So a conjecture is a statement that is believed to be true, and we can use reasoning to investigate whether a conjecture is true. So an example of a conjecture would be something like the idea that every October it is raining and cold. Okay, something I believe to be true, and it's just my statement. Okay, so let's go forward with this idea of thinking that every October is rainy and cold. All right, inductive reasoning is the process of reasoning that a rule or statement may be true by looking at specific cases. So if I wanted to go through and use inductive reasoning to prove my statement true, you need to look at specific cases. So for my conjecture of every October is rainy and cold, what we're going to do is go back and look at past Octobers to state whether or not it's rainy and cold in October. Now, deductive reasoning is the process of using logic to prove whether or not all cases are true. So if we think about our October example, so every October being rainy and cold, okay, if you use logic and we think about it logically, okay, are most Octobers rainy and cold? Probably, but is it logical to say every October is rainy and cold? No, it is not. Okay, and we could probably go back through using inductive reasoning to find a case where it's not. It may be a pattern, but it wouldn't be a conjecture that every October is. All right, postulates are statements you accept are true. An example of a postulate would be the segment addition postulate or angle addition postulate. Those are just things we accept as truth or as fact. They're recognized as the building blocks of geometry. Now, a theorem is a statement that you can prove is true using a series of logical steps. Now, these steps, we can use deductive reasoning, we can talk about definitions, mathematical relationships, postulates, or other theorems that we know to be true to help us prove that that is true. And oftentimes that process is how we go through and prove a lot of stuff in geometry. And we'll talk about how to do that. An example of a theorem that you may be familiar with is the Pythagorean theorem. Okay, it's something that we need to go through and prove, which has been proven to be true. And because we can prove that to be true, we can use it. So, we'll talk more about that throughout. Something just to be aware of with proofs. Before in geometry, it was something that was a long, drawn-out unit. We've now mixed it in and intertwined it throughout different sections. Before, it was a pretty big emphasis in geometry. Now we've shortened that, and it's just intermingled here and there. It's not something that's a big thing you need to worry about, and it's not a huge emphasis in the class. All right, let's talk about a few more things. A counterexample is our next point. So a counterexample is an example that shows a conjecture to be false. So a counterexample to my conjecture would be I just had to find one October where it's not rainy and cold. And then that's a counterexample. Another example, if I had a conjecture that every time you add two numbers, you get an even number as your result. Okay, so like if I added 2 plus 2, I get 4. 4 is an even number. But if I do 1 plus 2, I get 3. 3 is not an even number. So that would be a counterexample. All right, next part. A conditional statement is a statement that can be written in the form of if P, then Q, where P is the hypothesis and Q is the conclusion. For example, in the conditional statement, if 3x minus 5 equals 13, then x equals 6. The hypothesis is 3x minus 5 equals 13, and the conclusion is x equals 3. So, whenever you have something in the form if P, then Q, okay, know that the statement after if is considered your hypothesis, and the statement after then is your conclusion. Now, we'll go through and practice that and kind of look at that a little closer throughout today's lesson. All right, with all that said, let's get jumping into our examples for today. So example 1 is going to ask us to use deductive reasoning to solve the equation. So we're going to go through and solve an equation, and we're going to justify each step. So it's not just solving, but we have to state what we did and how we did it and why we could do that. So to do that, we are going to use the properties of equality. Now, properties of equality is something you have hopefully seen before in math class, whether Algebra 1 or a pre-algebra class. We're just going to briefly highlight them and run through them before we start using. So, our first property of equality is the addition property of equality. And what that states is that if I have A equals B, then if I add C to both sides, A plus C equals B plus C. All that this property is stating is that I can add the same thing to both sides, and it's still a true statement. So addition property of equality, I can add a number to both sides. Subtraction property of equality, I can subtract numbers to both sides. Multiplication, I can multiply the same number to both sides, and then the same thing with division, just that I can divide to both sides the same number. So addition, subtraction, multiplication, division properties of equality are just whenever you apply that to the formula that you are solving. All right, the reflexive property of equality is saying that something is equal to itself. So in this case, A equals A. And I know it seems really dumb to have to say a property to say that something is equal to itself, and I'm really going to highlight and star this property, because honestly, out of all these properties in geometry, this is the one you are going to use the most. And you'll see it pop up when we talk about proving triangles congruent. When we get to that module, in module 5 and 6, I believe, this does pop up quite a bit, and it is actually a very handy thing. So if triangles share the same side, okay, I can say that the side AB is equal to AB based off the reflexive property. It's just a point of formality and something we need to do, but this is one you do want to remember. All right, symmetric property of equality is stating if A equals B, then B equals A. So it just means that we can flip the stuff across the equal sign. Oftentimes, how you would see this is if you have 3 equals x, well then I could switch it to x equals 3. Okay, sometimes problems are going to ask you to have x equals as the starting point, and to be able to do that, you'd have to use the symmetric property to be able to flip it. All right, next, the transitive property of equality is if A equals B and B equals C, then ultimately A equals C. So transitive property is going to pop up here and there. I like to think of the transitive property as getting rid of the middleman, meaning A equals B and B equals C. These both share B, okay? So if they both share that, and that's kind of an ending and starting point, well, could I not cancel those out and then jump to just say A equals C? Well, that's what the transitive property is doing. It's identifying the middleman, cutting it out, and just jumping to the conclusion. All right, substitution property of equality states that you can take any number or any value for a variable, say x, y, a, b. You can take that with the substitution property and you can plug it in. So that means if I'm told x equals 3, I could substitute 3 in for x and go through and simplify my equation. So that's what substitution is. All right, so now that we have gone through and talked about the properties of equality, really the main ones you kind of need to be able to have an idea of is reflexive, symmetric, transitive, and substitution. Adding, subtracting, multiplying, and dividing, you should feel fairly comfortable when you use those properties. Know how to use them, know how to recognize them. That's the main thing when you get to a quiz, is you'll have to be able to go through and identify what happened in each situation. All right, example 1 is going to have us use deductive reasoning to solve the equation, and we're going to use properties of equality to go through and justify each step. So example 1a is 14 equals 3x minus 4. So what we need to do is go through and solve this equation like you're used to doing in algebra and pre-algebra. The only thing is we just have to provide a justification for each step. So if we have 14 equals 3x minus 4, okay, we have to solve for x and figure out what x equals. So our first step in this is we need to get rid of this minus 4. And if you recall from algebra or pre-algebra, we have to do the inverse of what's happening, so the inverse operation. So because this is minus 4, that means I need to add 4 to both sides. And when I add 4 to both sides, 14 plus 4 is going to be 18. So write it out for you. So we get 18 equals 3x because the 4's cancel out. Well, I went through and did that, but how can I state that I can actually do that? Well, our reasoning for this, because we added to both sides, is the addition property of equality. Okay, because I added 4 to both sides. All right, I now have 18 equals 3x. So I need to go through again and get x alone. So I need to do the inverse. 3x implies 3 times x. So the opposite of multiplication is division. So we're going to divide 3 to both sides. And when I do that, we get 6 to equal x. Because 18 divided by 3 is 6. Well, how can I say what I just did is allowed? Well, we're going to use the division property of equality. All right, now in some cases you could consider yourself done because I know what x equals, just part of a mere formality because I want you to see it in case it pops up on the homework or quiz. Sometimes they want you to have it as x equals in the front, so we have 6 equals, not x equals. So all we're going to do is just flip it to be x equals 6. And from the properties of equality that we talked about up above, that is the symmetric property of equality. And that's our answer, and that is how we go through and solve for this problem. So that is how you do example 1a. We're going to go through and solve using the properties of equality, and we have to go through and justify or give our reasoning for each step. I know it seems redundant, I know it seems drawn out. This just gives you kind of an idea of how to see it done with an example that you feel more confident about. Again, proofs are not going to be a huge emphasis, but it's something to be aware of. All right, so for matter of time, I'm going to leave part B for you to do on your own. You can always take a look at the completed notes if you need some extra guidance or reference, or just let me know if you want me to go through it later. All right, so with that said, we're going to move on to our next part. And what this part is going to do for example 2, I've kind of gone through and highlighted different problems you're going to see on the homework, so that way you can have an example of each of them. All right, so example 2 is going to ask us to explain why the given conclusion uses inductive reasoning. So inductive reasoning is going to have us go based off of observations. So that means that you have to go through and state why this uses inductive reasoning. So you just have to go through and give an example of how. So for example 2a, it asks us to find the next term in the pattern 1, 2, 2, 4, 8, 32. Now it states the next term is 256 because each number, starting with the third number, is the product of the two preceding numbers. What this means is my third number here, which is 2, okay, this is the product of the two numbers before it. Product means multiply, so 1 times 2 gives me 2. How do I get 4? Well, the two numbers before, 2 times 2 is 4. For 8, 2 times 4 is 8. For 32, 4 times 8 is 32. So then 256 would be a result of doing 8 times 32. And that is, in fact, what the answer is. So, how we're going to go through and state this. And instead of writing it out step word for word, I'm just going to put down what my answer key shows, which states that the conclusion is based on observing the pattern starting at the third number for 4 numbers. So it's not that we've just looked at one specific case, but we've actually gone through and stated this for 4 different cases that I know this to be true. So that would be how we use inductive reasoning on this, is that we actually looked at the pattern, we observed what happened, and then we found that to be true for at least 4 cases. And that could continue on. All right, if we look at B, so B states it always seems to snow on Christmas Day. So how can we use inductive reasoning for this? Is the conclusion is based on a limited number of observations. Okay, if I'm making this conjecture that it always seems to snow on Christmas Day, I am just using the number of observations I've had in my lifetime. So if you're 16 years old, you're basing that conclusion based off 16 observations. Now, in your life, that seems like a lot, but in the grand scheme of life, 16 years compared to, say, minimum of 2020 years isn't a whole lot in the grand scheme. So, while it seems like a lot to you, 16 years, in the grand scheme of life, that's really not a ton, and it's based on a limited number. All right, so with that said, let's kind of jump into our next part. So our next part is we're going to go through and talk about some different types of angles. So we're going to look at a lot of terminology today that's going to carry on throughout class. All right, supplementary angles are angles that add up to be 180 degrees. Okay, this is really important to know. Okay, and I'm going to highlight it when it comes back up, but know that supplementary means they add up to be 180. Now, complementary angles are angles that add up to be 90 degrees. Again, another thing really helpful to know. Adjacent angles are angles that are next to each other. They have a common vertex and side, but they do not overlap. Okay, I'll highlight an example of an adjacent angle, but they're angles that are next to each other, they share a side, and that's kind of what they are. All right, a linear pair is a pair of adjacent angles whose non-common sides are opposite rays. A linear pair means that they form a line. And in fact, they form a straight line. So whenever you hear something talk about a linear pair, the set of angles are a linear pair, that means they form a straight line for matter of purposes. All right, now let's talk about a theorem. So the linear pair theorem states if two angles form a linear pair, so angles 3 and 4 form a linear pair, that means they form a straight line here, just like this. And then that means they are supplementary, which, as we talked about above, that means they add up to be 180 degrees. So what it states is the measure of angle 3 plus the measure of angle 4 equals 180. So a linear pair, just to kind of shorten this, a linear pair is supplementary. So if two angles form a straight line, they add up to be 180. All right. Also, this is a great point to talk about adjacent angles. Angles 3 and 4 are adjacent because they share a common vertex right here, and they also share a side. So 3 and 4 are adjacent because they are right next to each other. Okay, if they are not next to each other, then they are not adjacent. All right, so example 3 is going to have us talk about counterexamples. And there's a couple different scenarios and situations that we have here. So for A, it talks about for any integer n to the power of 3 is greater than 0. So what that probably means is any number that you put to the power of 3 is going to be greater than 0. So an example of that would be you just have to go through and try different numbers to see if that's the case. For B, two angles that are supplementary have to have different measures. So two angles that add up to be 180 have to be different numbers. Okay, can you give an example of two angle measures that can be the same that add up to be 180? And then C is that all prime numbers are odds. Means you just have to decipher whether there's a prime number that is not odd, and you can figure out for that. All right. For this, because you can go through and take a look at all these done in the completed notes, I'm just going to take a look at one of them. And for this one, we're going to take a look at part B. So stating that two angles that are supplementary have to be different measures. Okay. So remember, supplementary means they add up to equal 180 degrees. So, is there a number from 0 to 180 that you can add to itself and it equals 180? So what two numbers that are the same can you add and get 180? Well, in this case, the counterexample would be 90 degrees and 90 degrees, because they're two different angle measures. Okay, so they're two angles, and they have to be this different measures. Well, these two are two different angles. They have the same measure, and last I checked, if you did 90 plus 90, you got 180. Well, 90 and 90 have the same measure. They are supplementary, so this is a false statement. So 90 degrees is my counterexample. Now, you can go through and probably find numerous different counterexamples for some different problems. Doesn't mean that you have to provide every single one of them. You just have to provide one that's false. So, I have two angle measures, and they are the same in this case. Therefore, this is a counterexample to this conclusion. All right, so moving forward, example 4 is going to have us go through and identify the hypothesis and conclusion for each statement. So what you're going to go through and do is take the conditional statement, and you're going to go through and state what is the hypothesis and then what is the conclusion. So this is that if P, then Q. Okay, and remember what we talked about before? P is the hypothesis and Q is the conclusion. So everything after the statement if is our hypothesis. Everything after the statement then is our conclusion. So, for example, for this problem, for part A, if angles are vertical angles, then they are congruent angles. So, the statement after if is angles are vertical angles, and then the statement after then is they are congruent angles. So our hypothesis is that the angles are vertical angles, and then our conclusion is going to be that they are congruent. Okay, you don't have to go through and prove whether or not this is a true statement. This is a true statement, but we're not worried about that. All this problem is asking us to do is identify the hypothesis and conclusion. Again, the statement after if is the hypothesis. The statement after then is the conclusion. All right, part B is going to have you do the same thing. It's just a different conditional statement. In this case, it's if an angle measures 90 degrees, then the angle is a right angle. So again, go through and identify your hypothesis and conclusion. If P, then Q. Statement after if is hypothesis. Statement after then is your conclusion. Now, I will leave that one for you to go through and do. And you can take a look at my completed notes if you want to check to make sure you have the right idea. All right, so with that said, we just have a little bit left. And the remainder of this page is going to be talking about different postulates relating to points, lines, and planes. So we're going to run through and talk about these. This is a great reference sheet to kind of have up while you work through stuff or just homework or for the quiz. All right, so our first postulate is through any 2 points, there's exactly one line. So it means if I have 2 points, there's only one straight line that can go through those 2 points, meaning there's no other line that I could draw that would be different than that line. All right, next, through any 3 non-collinear points, there's exactly one plane containing them, meaning if these points are not on the same line, there's exactly one plane that can contain them, like this. All right, next one. If 2 points lie in a plane, then the line containing those points lies in the plane. So if there's 2 points in a plane, then the line that goes through those points is also in the plane, meaning that it's not going to shoot up out of the plane because it only runs through those 2 points, so it has to be in that plane. All right, next one. If 2 lines intersect, they intersect at exactly 1 point. So if I have 2 lines that are going to cross over each other, they cross at only 1 point, in 1 point only. All right, last one states if 2 planes intersect, they intersect at exactly 1 line. Okay, think about it. If you could place a piece of paper through another one, okay, it's going to cross at a line. So that cross or that cross section is going to be a line. So a point cross, or 2 lines cross at a point, 2 planes cross at a line. All right, so with all of that stated, we're going to go through and kind of practice identifying different stuff for that. All right, example 5 is going to have us go through and use the figure to name each of the results described. So if we look at this, we're going to use our diagram right here to help us go through and find an example of each of these. So the first one is we need to find an example of the line of intersection between 2 planes. So remember that two planes are going to cross at one line, and these two planes are actually going to cross at this line. So the example from this figure is going to be the line FG or GF. All right, the next one talks about the point of intersection of two lines. Well, I have a line FG and a line HJ right there. Well, these two lines are going to cross at the point J. So my example is point J. Now, three coplanar points means that I need to have 3 points that lie on the same plane. My example that we're going to go through and do for this one, so we're going to say points. I'm going to use points F, J, and H, okay, because these all reside in this plane. So points F, J, and H. Are 3 coplanar points. You could say F, J, and G, or H, J, and G. All of those work as examples. All right, 3 collinear points. Collinear means they all reside on the same line. So we have to find 3 points that reside on the same line. And we're going to go with points F, J, and G. All right. So with that said, we only have one more example to go. And I know this has been a lot of examples, but hopefully using this in the completed notes will help guide, because I've tried to hit about every type of problem you'll see for today. All right, example 6 is going to ask us to use deductive reasoning to write a conclusion. So for part A, it states, if a number is only divisible by 1 and itself, then it is a prime number. The number 43 is only divisible by itself, or by 1 and itself. So, first thing, notice what is common. Okay, we have this part, if a number is only divisible by 1 and itself, shows up down here as well. So, kind of go through and highlight the parts that are common. Okay, so this part that a number is only divisible by 1 in itself, these two things are in common. Well then, the part that is remaining, the number 43, and then it is a prime number. So what you're going to do is you're going to take these two, and that's going to be your conclusion. So how we're going to set this up is we cancel out the part that's in common, and then we just take the number 43 is a prime number. I didn't mean to put a comma. All right, so all I did is I went through and highlighted what was the same. We kind of cancel that out, and then we take the two parts that are remaining, and we write a conclusion. And our conclusion in this case is the number 43 is a prime number. All right, if we took a look at B, kind of carrying the same idea. So we have, if two lines intersect, then they intersect at one point. And then we have lines A and B intersect. So the common part is if two lines intersect, okay, and parts A and B intersect. So then the non-common parts is they intersect at one point, and lines A and B. Okay, two lines intersect is common. So how we're going to write this is we're going to take the first part of the second statement, lines A and B, and then we're going to take the second part of our first statement, intersect at 1 point. And that is how you're going to go through and use deductive reasoning to write a conclusion. I would really suggest when you get to these problems that you either pull this video back up to this part, or you go through and look at the completed notes to again see what that's going to look like. So again, you're going to identify the common part, you're going to cancel it out, and then just form a conclusion with the two parts of the statements that are not used or the same. All right, so with that said, that is your video for section 1.4 on reasoning and proof. That's your introduction. I know this is a lot of different examples, but this should give you an overview of what you're going to see in the homework and on a quiz upcoming. So, reminder before I sign off on this one that section 1.4 is the final section of module 1, and to just be aware, that means a quiz is on the horizon. So be on the lookout for that and be ready for that up ahead. So with that said, that is all that I have for you guys today. Thank you for listening, and I hope this was helpful for you. I will talk to you guys later.